Welcome to this tutorial that describes the difference between Cwdm and Dwdm. Before looking at the different variants of WDM technologies, we need to know more about the characteristics of the optical fiber that transports the wavelengths in a WDM system. When a light wave moves along a glass fiber, some of its energy is lost, so the wave amplitude becomes smaller and smaller. The wave is attenuated, and at some distance, the amplitude is so small that the wave cannot be detected at all. The signal is lost. The attenuation depends on the quality of the optical fiber, but also on the wavelength of the light. Some wavelengths are attenuated more than others, and are therefore less suitable to use in an optical communication system. The solid black line in this chart shows the attenuation per kilometer for different wavelengths when transmitted over a typical optical fiber. The attenuation curve is rather flat and low for certain wavelength ranges, but has higher peaks for other ranges. Wavelength regions with low attenuation are often referred to as the transmission windows of the optical fiber. These low attenuation transmission windows are the ones we want to take advantage of for a WDM system. Using the transmission windows can be done in two different ways, depending on how much bandwidth each wavelength is allocated on the optical fiber, giving us either coarse WDM or dense WDM, that is, Cwdm or Dwdm. WDM, in its most original version, used only two wavelengths, 1010 and 1550 nanometers, for two channels on a single fiber. This was useful in cable TV systems, where you stream a TV channel in one direction and send control information in the other. Rather, soon the need for more channels was pressing, and in 2002, a grid of 18 wavelengths in the 1270 to 1610 nanometer span of the spectrum was standardized for WDM by the Telecommunications Union ITU-T. To enable the use of less sophisticated transceivers, each individual channel can use a reasonably broad part of the spectrum, being separated 20 nanometers from the next. This coarse dividing of the available bandwidth consequently was named coarse WDM, or Cwdm for short. Cwdm has 18 wavelengths, which can be used as 18 channels in one direction, or as 9 full duplex, bidirectional channels over a single fiber. As can be seen from the diagram, some of the Cwdm wavelengths lie in an attenuated region called the water peak of standard optical fiber. Cwdm has turned out to be a convenient solution for medium-capacity optical links at short to medium distances. It is, for example, often used to transport 1 and 10 gigabit Ethernet and 16 gigabit fiber channel in legacy installations. However, Cwdm has a major drawback. The wavelengths are not spaced appropriately to be amplified by optical amplifiers, so when the signal has died out, it cannot easily be amplified again. This limits the Cwdm reach to less than 70 kilometers for a 2.5 gigabit per second signal. Dense wavelength multiplexing, Dwdm, uses a smaller range of wavelengths than Cwdm, but with a much denser channel spacing of only 0.8 nanometers or less. With this channel spacing, it is possible to accommodate 40 channels or more over a single fiber strand, with the channels used either all in one direction or for full duplex traffic. The Dwdm channels are located in the 1530 to 1565 nanometer wavelength range, called the C-band of the fiber. Hence, there is an overlap between the Dwdm channels and some of the standard Cwdm channels. Dwdm systems must maintain more stable wavelengths than those needed for Cwdm because of the closer channel spacing. This originally meant higher costs for Dwdm systems than for Cwdm systems, but technology advances and mass production have now made it possible to provide Dwdm systems at similar or lower price levels as Cwdm systems. A major advantage of Dwdm is that optical amplifiers can be inserted along the fiber, making it possible to bridge virtually any distance between sites. Dwdm systems are also available for much higher data rates than Cwdm systems, which means that each channel can handle 400 gigabit per second or even higher speeds. The number of channels in a Dwdm system depends on how closely the wavelengths are spaced. If wavelength spacing is decreased, more channels can be accommodated. The wavelengths to use is defined by the ITU-T recommendation G694.1, which defines a grid of 40 channels 0.8 nanometers apart. It is possible to build DWDM systems with less channel spacing and therefore more channels, for example, with 80 channels. However, as each channel is provided with less and less spectral space, the maximum number of bits per second that can be transmitted over the channel decreases. So, for high data rates, such as 400 gigabit per second, another wavelength allocation technique called FlexGrid has become popular. With DWDM FlexGrid, the available spectrum is divided into small slices, which can be allocated in variable size groups as contiguous spectrum slots for each channel. This means that high-speed channels, such as 400 gigabit per second channels, can be given enough bandwidth, and that channels can be squeezed more closely together, making optimal use of the available spectrum and increasing the overall optical link capacity. High-speed channels using DWDM FlexGrid can easily be deployed on an already existing fiber infrastructure. This is a good example of how DWDM technology protects already made investments and takes advantage of new advances in transmission technology once the transceivers become available. CWDM and DWDM can also coexist on the same fiber. Since the DWDM wavelengths overlap some of the CWDM wavelengths, a part of the available spectrum can be allocated to DWDM channels and the rest to CWDM channels. By combining the technologies in this way, you can gradually phase out an existing CWDM system and replace it with a higher capacity DWDM system. It is just a matter of switching the transceivers for relevant CWDM wavelengths to higher capacity transceivers for DWDM at the endpoints without any need for changes of the fiber network in between. So, what should you choose? CWDM or DWDM? Well, it depends on your requirements and what you already have installed. This table summarizes some of the characteristics of each technology. Talking generally, we would recommend that you take a closer look at the DWDM technology, being the most modern and providing you with the best upgrade path for future capacity needs. This ends this tutorial. To learn more about optical communications, just continue with the next tutorial in this series.